This video covers section 1.1, review of functions. We have 5 objectives. We'll start by identifying whether a relation is a function. We will look at finding domain and ranges of functions. We will do the composition of functions. We will look at secant lines and the difference quotient. And then finally we will do symmetry of functions and also look at even and odd functions. So let's start with defining what a function is. So I've written 3 separate definitions here for what a function is. A function can be defined as a set or a rule or a mapping that has certain properties. These are all equivalent definitions. They're just defining it on a separate object. So I'm going to focus just on this third option here. We can think of a function as a mapping between 2 sets, a set of inputs and a set of outputs, and the condition for it to be a function is that whenever you take an input element, it can only be mapped to one output element. So if we look at this is a typical mapping diagram here. These are our set of inputs, which we call the domain, and every input gets mapped to one and only one output. Now what people get confused with usually is here we have 2 separate input elements. They both get mapped to the same output. That's okay. What we can't have is we can't have an input that gets mapped to 2 separate outputs. This x value, if I included this arrow here, it's mapping to this point, but it's also mapping to this point. And for a function, that's not allowed. Now, again, just to reiterate, we said the domain is the set of all input values. We also can define it as the set of all possible values of the independent variable. And then the range is the set of all output values, or the dependent variables. The output depends on what the input is. So that's where these 2 words come from. You are free, you are independent to pick. The choice that you plug in is independent, but the output value depends on what you plug in. You may also hear the term argument thrown around. So argument of a function is really just saying what is the function being evaluated on. So if you look at the function notation here, remember f is the name of the function and the input is right here. This is the argument. The argument is x. So let's do a quick review of function notation. So here we have our function f of x equals x squared minus 2x. Remember that this notation does not mean f times x. This is simply the name of the function and this is the argument. It's what we're plugging in. So the first one says to do f of negative 1. Now whenever I see function notation like this, the way I think of it is the x's are all like input boxes. Every x in the function is an input box, and whatever is written here has to get plugged into these boxes. So if we're doing f of negative 1, we have to put negative 1 in each of those boxes. And the boxes, really, you should think of them like parentheses. So we have negative 1 squared minus 2 times negative 1. Squaring the negative 1, you get positive 1, and then these 2 negatives make a positive, so that'll become plus 2, which gives us 3. So when you plug negative 1 into this function, you get out 3. Alright, we can also do examples where the argument is algebraic. So here we're plugging in x squared. So again, x squared is going in these 2 boxes here. So we have x squared squared minus 2 times x squared. And then we just simplify here. Power raised to a power, you multiply the powers. So that's x to the 4th minus 2x squared. And that's it. These are not like terms, can't combine them. So when you plug x squared into this function, you get out this new function. Alright, let's try one where we change the variable. So this says evaluate the function at t. Well, we're going to put t in the boxes. And you can see all that does is it just changes out what the variable is. So 2t squared minus 2t. And then the final one, we're going to evaluate the function at the expression p minus 1. So f of p minus 1 equals the quantity p minus 1 squared, in parentheses, minus 2 times p minus 1. Okay, here be careful. Remember that when you're squaring a binomial, you don't get to just square each of the terms inside. This actually means p minus 1 times p minus 1, and so you have to FOIL that. So if we FOIL it, we're going to get p squared minus 2p plus 1, and then you can distribute the negative here, minus 2p plus 2. And then this one we do have some like terms, so we have p squared minus 4p plus 3, and that's it. So this is what we get when we plug p minus 1 into that function. Okay, a couple more things. A lot of times you will hear phrases like this: y is a function of x, or it might just be something like blank, like might be area is a function of radius. So think of these as blanks. Anytime you see blank is a function of blank, it means y depends on x, y is the dependent variable, x is the independent variable, or in other words, y is the output, x is the input. When y is a function of x, we're saying that the second thing here, this, is the input. And then it also implies this notation as well. Y is a function of x. Okay, a lot of times our functions are going to be represented with graphs in the xy plane. And we said we're typically going to have x being the input, and we're going to have y being the output. And we said in order to be a function, if you pick any input value, let's actually do it over here with this one. So let's say this is my input value. It can be mapped to one and only one output value. Let's call this b. So according to this graph, f of a is equal to b. But if we come back to this one, if I call this a, well, it gets mapped to two separate y values. Let's call it y1 and y2. This can't happen. In order to be a function, when you plug a in, you can only get one output, but this one has two. So one way to visualize that is we have a vertical line and it's intersecting the graph in 2 points, and that is going to be an indicator that the graph does not represent y as a function of x. So this we call this the vertical line test. So anytime a vertical line intersects a graph in 2 or more points, it cannot represent a function, at least not y as a function of x. On this one, draw yourself a vertical line, and no matter where I move that vertical, it's not going to let me do that. No matter where I move a vertical line back and forth, it's only ever going to cross in 1 point. Okay, so let's go through these and see which ones represent functions. So if we look at this first one, imagine drawing a straight line. Let's see if I can do it with this tool here. Yeah, let's see if it'll let me move it. Okay, that works. Okay, so no matter where I move this vertical line, it's only ever intersecting the graph at most 1 point, and at most 1 point. So this one is a function. If we come to the second one though, bring our vertical line over, we can see clearly it's intersecting at 2 places, so that one is not a function. Next one. It's not going to let me do it now. There we go. Okay, bring my vertical line. It only ever crosses in at most 1 point at one time. It's only hitting it at 1 point. So this one is a function. And then the final one you can see definitely not a function. So here it actually intersects at 3 points. So definitely not a function. And again, just to be perfectly clear here, when we say function, we mean y is defined as a function of x here. It is possible, this one's would almost work, but it doesn't quite work, where you could say that x is a function of y, and, if you flipped this over. But for the purposes of this course, we're always doing functions of x for now. So vertical line test suffices. Okay, so next example says to graph the functions on a graphing calculator and then state the domain and range. Now, I went ahead and just included the graphs here so we don't have to pull the calculator up. A lot of times on MathXL you are going to see windows like this. What this is telling you is that the x min is -3 and the x max is +3. The y min is -1 and the y max is 5. So you can adjust those by pressing the window button at the top of the calculator. Okay, now for the domain and the range, they don't actually want us restricting to these intervals. They want us to think of the whole function. So we should be able to do this without a graphing calculator. We should understand this is the squaring function, should look like a parabola shifted up 1 unit. We know that this graph goes up towards infinity on both sides, and we also know you can plug in any real number that you want. So the domain is just negative infinity to positive infinity, all real numbers. One way to think about this is, I tell people to think about painting the entire function a color. Got red paint all over the whole thing. And then we're going to take a trash compactor and we're going to squish this thing down onto the x-axis, just pushing it straight down. And all of the x-axis that has paint on it would be part of the domain. And since this goes up and out forever, the entire x-axis would be covered in red paint. So the domain is everything. Okay, range. To get the range, we kind of think of smushing it onto the y-axis, pressing it this way, and what would be covered then. And we can see the range is from 1 up to infinity, and 1 is included, so 1 to infinity. Okay, next function is this one here. If you didn't already have it graphed, hopefully you would recognize that this is the upper semicircle of a circle centered at the origin of radius 2. Remember that the equation of a circle centered at the origin is x squared plus y squared equals r squared. If you solve this for y, you get y equals plus or minus the square root of r squared minus x squared. Plus is for the upper semicircle, minus the negative is for the lower semicircle. So this matches that. Okay, so we can see then, based off of the graph, the domain is going to be negative 2 to positive 2. And the range is going to be right here. It's going to be from 0 up to 2. All right, and then the final one is a rational function. And again, we should be able to tell the domain just by looking at this. When you have a rational function, you have to throw out anything that makes the denominator equal to 0. So we can see that we need to throw out that u cannot be equal to 1. So the domain is going to be everything but 1. So negative infinity up to 1, union 1 to infinity. So you can kind of see that here. Imagine again, put red paint on the graph, and then if we smash it all down onto the x-axis, there's going to be a hole right here. Everything would have red paint on it except this number right here, be missing from that vertical asymptote. All right, and then for the range, you can think of it kind of the same way, except we're smashing it this way. Everything on the y-axis is going to be covered in red paint except for the origin right here. There's no way for the output of this function to be 0. No matter what you plug into it, it's always going to be a non-zero number. The only way it could be 0 is if the numerator was 0, but the numerator is a constant number. So the range is everything but 0. So negative infinity up to 0, union 0 to infinity. Okay, one more example. This was one that has an actual context or a story to it. So it says at time t equals 0, a stone is thrown vertically upward from the ground at a speed of 30 meters per second. Its height above the ground in meters, neglecting all air resistance, is approximated by this function here. And that function is, the output is measured in seconds. It says find the domain and range of this function as they apply to this particular problem. So what they mean by that is, if we just think of the function without the context of the problem, then this is a polynomial. And as we've stated in previous courses, we know that polynomials, the domain is all real numbers. But that doesn't make sense for this physical problem. For example, the input is time. And it does not make sense for the time to be negative. So we would assume time is going to start at 0. So the domain is going to start at 0. And then the output of this, the entire expression, represents height. So what we would need to think about is, well, it only makes sense for height to be a positive number. So what t values make it positive? Well, as you can see from the graph here, the height is positive from 0, or non-negative I should say, from 0 out to 6. Right, we could easily find those by just solving the inequality 30t minus 5t squared is greater than or equal to 0, but we can see it from the graph there. So these are the only input values that make sense. T should be something between 0 and 6 because that's when the height is non-negative. Okay, and then for the range, we can also see that from the graph. The initial height, remember range values are heights here, well the initial height is 0, and the height goes all the way up to this point here. Now we can find that point by just evaluating h of 3, which we could see is 30 times 3 minus 5 times 3 squared, which gives you 90, minus, this is going to be 9 times 5, which is 45. 90 minus 45 is 45 again. So 45 is the maximum height of that function. So our range, the heights go from 0 up to 45. Okay, let's look at another function here. It says, what's the domain and range of this? Now, you could graph it. You could try to identify it from graphing it, but let's try to do this without that, just by analysis. So we have a -1 exponent, which means that we need to take the reciprocal. Right? Negative exponents mean reciprocal, so this really is this function, 1 over x squared plus 1. So to find the domain, we need to, since it's rational, we know that bad things could happen if the denominator is equal to 0. So if we set that denominator equal to 0, try to solve this, anything that solves this would need to be thrown out of the domain. So hopefully you can already see what's going on here, but we're going to end up with plus or minus the square root of -1, or plus or minus the imaginary constant. For this course, we are dealing with only real numbers, so we're not allowed to use these to begin with. So what that means is there is no way to make this undefined. There's no way for us to make the denominator 0 because we're not allowing imaginary numbers. So therefore, you can plug in whatever you want. Nothing bad can ever happen, so the domain has to be all real numbers. Okay, range is always trickier, especially if you don't know what the graph looks like. But if we kind of analyze this, one thing we should notice right away is there any way that this expression could come out as a negative number? Well, the top is always positive, and if we look at the bottom, we are squaring the input. So no matter what type of number I plug in, the x squared part's always going to be positive, and then, or non-negative I should say, and then we're adding 1 to it, which means the denominator is always going to be a positive number. Top's positive, the bottom's always positive, so the output of this can never come out as negative. So then the next question is, well, could it be 0? Is there any way to make this function equal to 0? And we can see again the answer is no. The only way it would be 0 is if the numerator could be 0, and it's a constant 1. So the range, it can go all the way down to 0, but 0 is not included. There's no way to make it equal to 0. So the next question is, well, how high can it go? What's the biggest number that it can be? Well, if we think about what is happening with this, so we have 1 and then we're dividing by this number. The bigger I make this number down here, the bigger the denominator is, which means the closer the fraction, the whole value is to 0. If I plug in 100 into the denominator, I'm going to get a very small number. If I plug in 1000, I'm going to get an even smaller number. So that's how we get the values that are close to 0. So putting in big X's doesn't make the function value big, it makes it small. So that means putting in small values should make it bigger. Well, what's the smallest value that we can plug into this? Well, negatives aren't going to, if you think of negatives as being small, in magnitude they're not, but when you plug a negative in, it's going to be the same as plugging a positive. So the smallest value we can plug into this is 0. And plugging in a small number here makes the overall fraction as big as it possibly can be. And you should be able to see if we plugged 0 into this, you're just going to get 1 out. The maximum value for that function is 1, and it does achieve it, so you include that one. So that gives us our domain and our range for that function. Okay, composite functions. So functions have a special operation, a binary operation, which we call composition. It's denoted by that symbol there. The definition, f of g of x, is just put g inside of f. So you can think of composition of functions as just like chaining them together. And order does matter here. So when you do f of g of x, it's different from g of f of x. The one that's closest to the x here is always the one that's applied first. Okay, so let's try doing this. Technically, I guess we've already been doing it before because we were evaluating functions before, but this could be thought of as a composition where we have this could be like g of p here. We're plugging that into this function. Okay, so this is going to be 3 times 5p plus 1 all squared minus, now here you have to be careful. Remember, think of this like input boxes. And this says to subtract the entire thing back here. So this is what's getting plugged into that box, which means it's got to be in parentheses. That's where the majority of mistakes would be made with this problem, is not putting this in parentheses. That negative needs to be able to distribute to all of it. Okay, so we need to FOIL here. So this is going to be 3 times 25p plus 10p plus 1 minus 5p minus 1. Distribute the 3, so we get 75. Oh, I forgot my square on that. Right, this came from multiplying this by itself. Should have been a p squared there. So 75p squared plus 30p plus 3 minus 5p minus 1. All right, and then combine like terms as so we've got 75p squared plus 25p plus 2. Okay, then let's come over to this one. So now we're plugging this into g. Now you can think of g as 1 over input box. And we're putting that into the input box. So this is 1 over x. Or in other words, it's 1 divided by 1 over x. Well, we know division, you just do keep change flip, so it's keep this the same, change to multiply, and then take the reciprocal. Division is multiplication of a reciprocal, which just gives us x for that term. Okay, so moving on. Now doing the composition f of g of x. Notice that this is the same as this. So we're putting g inside of f. So let's go ahead and write in g. G is 1 over x. So that is getting plugged inside this function here. So that would be 3 times 1 over x all squared minus 1 over x. So we have plugged it into that function. Now, we could go ahead and simplify this. If we're going to square that first term, that's 3 times 1 over x squared. Right? When you square this, you're doing 1 over x times 1 over x, which would just be 1 over x squared, minus 1 over x. And then you'll get 3 over x squared minus 1 over x. If you get a common denominator, then you have 3 over x squared minus x over x squared. And that gives us then 3 minus x over x squared as the simplified form for that function. Okay, and then reversing the composition, putting f on the inside, this is g of 3x squared minus x. And this one's even easier because g is just 1 over input box, right? That's what g is, and this is what goes in the box. So 1 over 3x squared minus x. Okay, now something that we will be doing more commonly is actually decomposing a function, meaning that this function, we want to think of this as being written as f of g of x. It's a composition. There's an inner function and an outer function. So when I look at this, what I see as the inside would be this piece here. So we're going to say g of x is 9x minus x squared. And then f of x would be the outer function, which would be the square root of x. If you compose these two functions, put this inside of this, you get back to this function. Okay, now it also says find the domain of the composite function. So to find the domain of this, we have to look for bad behavior. So bad behavior in this example would be anything that makes the radicand negative. So in other words, we need 9x minus x squared to be greater than or equal to 0. The radicand part, just what's under the square root, needs to be greater than or equal to 0. Okay, so this is a quadratic inequality. To solve it, I'm going to go ahead and solve the related equation, 9x minus x squared equals to 0, to find what I've called in previous courses the critical numbers. We'll have a different meaning for that this year, but we can keep using it for now. So take out the x, and you get 9 minus x left over there. So our two numbers where it changes sign potentially are 0 and 9. Now if you think of this in terms of a graph, so we have one of them here and one of them here. As a function, this would be a frowning parabola, like that. And we wanted when it's positive. Well, it's positive between here and here. This is where it's positive. So that's what we need to keep, which means the domain is 0 to 9. These values out here would make this expression negative, would make g negative, and we can't take square roots of negatives. So that's our domain. Okay, moving on to example B. Again, we're going to start by finding an inner function. This actually has several options. So one would be we could just take x squared minus 1 as the inner function, just this. That would make f of x equal to 2 over x cubed. Now, one thing about these types of problems is your answers are not unique. There's not just one answer that you can use here. So, for example, a different option would be you could say g of x is x squared minus 1 all cubed. And then f of x would simply just be 2 over x. So, different functions, but they give the same composition as this. Okay, last is to find the domain of this. So for the domain on this one, it's a rational function, so we need the denominator to, we can't have the denominator being 0, so we would set x squared minus 1 equal to 0. Okay, technically if you're confused, you could set this equal to 0, but the very first step that you're going to do is take a cube root of both sides, so you'd get x squared minus 1 equals the cube root of 0, which obviously is still 0, so you might as well just go straight to x squared minus 1 equals 0. This is a difference of squares, so you get x minus 1 times x plus 1. So we get the numbers that have to be thrown out are 1 and negative 1. Right? These are the numbers that would make the denominator 0, so they need to be thrown out of the domain. So the domain will be everything but those. So it'll be negative infinity up to negative 1, union negative 1 to positive 1, union 1 to infinity. This is going to be the preferred way that you write this, but there may be examples where they have you do set builder, which is actually shorter for this one. So the set of all x such that x is not equal to negative 1 and x is not equal to positive 1. So either of those are satisfactory. Okay, so a couple more examples of composite functions. So here f is the cube root and g is this polynomial here. So the first one we're going to do is g of f of x. So remember, when you write this out in the normal format, it's whatever's closest to the x's on the inside. So g of f of x, just like that. So g, and we'll go ahead and put f in, it is the cube root of x. So this is getting plugged into this function. So we would have, let me start with some parentheses, put cube root inside there and square it, that's plugging that in, minus the cube root of x minus 6. This is technically the answer. This year we're not going to be very fond of the radical notation, so we would probably rewrite this as x to the 2/3. Remember that cube root is a rational exponent of 1/3, and when you have power raised to a power, you would multiply them. So cube root squared is really x to the 2/3 minus x to the 1/3 minus 6. For us, this is going to be an easier type of function to deal with than using the radical notation. Alright, now you can also compose a function with itself, so g composed with g is g of x. So we are putting this function inside of itself. So this is going to get kind of messy here. So we have to plug this into the square part. So x squared minus x minus 6 all squared, that's just putting it in here, minus the function itself, x squared minus x minus 6, that's putting it in there, and then we have the minus 6 at the end. It's x squared minus x minus 6, where we've replaced x by the function itself. Okay, so now we need to go ahead and clean this up. Okay, so in order to do that, we need to multiply this by itself. So it's going to be messy here, you just use distributive property. So if I send the x squared through, we would have x to the 4th minus x cubed minus 6x squared. That was distributing this to all the terms. Now we're going to distribute the negative x, so be careful with your signs here, minus x cubed plus x squared plus 6x. So that was distributing the negative x, and then we can distribute the negative 6 all the way through. So we would have minus 6x squared plus 6x plus 36. So all of that was just expanding this. Then we have to run a negative through here, so minus x squared plus x plus 6 minus a 6. Okay, now we have to combine like terms. So x to the 4th, that is the only one that we have. X cubed, we have, looks like these two here, so minus 2x cubed. Then squared terms, we've got negative 12 here, plus this one, so it looks like negative 11x squared. Oh, did I miss one here? I did. Actually, these canceled, so that's still 12. Okay, then we need the x terms. So we got one here, one there. So we've got, that one is 13x. And then these cancel, so it looks like it's going to end with a 36. So hopefully we didn't miss anything. Let me double check my notes here and see if it matches. Alright, looks like it matches. Okay, so you can see they can get pretty messy. Okay, definitely going to see something like this on, I believe, the first assessment. So this is where we're going to use just the graph to do compositions. These should actually be pretty easy, but I know that students oftentimes find it confusing if they haven't seen this type of thing before. But it works the same way. You just have to read the graph. So we're doing f of g of 5. We work from the inside out. So the first thing is plug 5 into g. So you go to the graph of g, plug 5 in, and this is the output. The output is 1. Right? So g of 5 is really a 1, which means we have to plug 1 into f. We plugged 5 into g, we got 1 out, now we're plugging 1 into f. So go to 1, plug it into f, and you get out 6. And that's how it works for all of them. So this next one, start by plugging 3 into g. 3 into g is 4, so we need to do f of 4, right? This entire thing was 4, so now we're plugging 4 into f. 4 into f is 8. Alright, next, now we're plugging 3 into f first, so 3 into f is 5, so we need to do g of 5. Right, this came out as 5. So now 5 goes into G and we get out 1. Then f of 4. So we need to plug 4 into f. 4 into f is 8. So then 8 into f is 6. So that's how that works. Now we can also do this with tables instead of graphs, and again works the same exact way. So first one, it says plug 0 into G. So this row here represents the input. So we're plugging 0 into G, we get an output of 2. If you plug 0 into G, you get out 2. So that means we're doing f of 2 because G of 0 was 2. Plug 0 in, G of 0 is 2. All right, f of 2. Go again to the input row. 2 plugged into f comes out as 2. Okay, next one. Plug -1 into f, you get out 1. This whole thing is 1, so we're really doing G of 1. And then plug 1 into G and you get out -3. Okay, now remember I take these problems from our textbook, and if you compare this to the textbook, you'll notice there is a typo. This should have been a -2 in order to match the textbook. It doesn't really matter, but just to make this last one a little bit more interesting, I'm going to go ahead and put that negative back in there. Okay, so now this has got 3 compositions. So we start by plugging -1 into G and we get out 0. Right? This is 0. So we have f of G, the second G has not been applied yet. F of G of 0, because all of that was 0. Okay, now we're plugging 0 into G and we get out -2. So this is, inside part is -2. So now we're going to plug -2 into f and we get out 0. So the final value after plugging all these in is 0. Right? This is like a sequence of machines. We plugged in -1, we got out 0. Then we plugged in 0, we got out -2. Then we plugged in -2 and we got out 0 again. Okay, next we're going to look at secant lines and the difference quotient. We have done this, if you've taken the previous courses with me, if you did college algebra and pre-calculus, we've done this in those same courses, but this is going to play a very big role in this course. So just to remind you, secant line, what we mean by that is if you have a function, any line that intersects the function in at least 2 points is a secant line. So we're interested in, given any function and given any point on the function, how do you find the slope of a secant line? And we're going to do this in 2 different ways. This is the same way that we did it in the previous courses. The one that we look at after this is a slight modification, but they both represent slope of the secant. So if this is our initial point, then we could say that its x-coordinate is x, and its y-coordinate would be f of x, right? So the coordinates for that point are really x, f of x. It's the x is obviously x, and then that's the y value. And then the way we're going to get our second point is we're going to say, okay, imagine that you move over h units. Okay, h, we're going to typically think of h as a very small number, but it doesn't really matter. Move over h units, and it could be moving h to the right, or it could actually be h to the left. This process will work the same way. If we moved to the left, h would just represent a negative number. Okay, so that means then that this x-coordinate would be x plus h. If we moved over to the right h units. To get the y-coordinate, we simply plug it into the function. So that's why we see the y-coordinate here is f of x plus h. Now, we know that in general, slope is the change in the y over change in x. Delta y over delta x, change. So that, in other words, it's y2 minus y1 over x2 minus x1. The change in the y over the change in the x. So, well, this right here is our change in y, the delta y. We need to subtract these 2 y values. So we do f of x minus h, plus h, minus f of x, and then we need to do change in x. Well, the delta x is actually this distance here, which you can already see is actually h, but let's say you didn't notice that. We would need to take this minus this. So x plus h minus the x. And you can see the x's then cancel, which gives us f of x plus h minus f of x all over h. So this is our slope of our secant, but it's also what we call the difference quotient for the function. We will be using this to build the thing that we call the derivative. Now, because we don't like anything to be easy, we have a different way, an alternate way of looking at the same concept. So the difference here is we're going to call the initial point A instead of calling the initial point x. And then we're going to say that the second point is actually just x. So that means that the coordinates of this point are a f of a, and the coordinates of this point are x f of x. So we've just kind of moved where they're at. We don't have an h with this one. But the concept then is still going to be the exact same thing. We need to do delta y over delta x, right? To get slope of the secant, it's delta y over delta x. Delta y is this, the difference between these two, so it's f of x minus f of a. And then delta x is this distance, which would just be the x minus a. This distance here is that number minus that number. This form looks a lot more similar to slope, the y2 minus y1 over x2 minus x1. Right? Its final form is basically the same thing. And it also should remind you of something we've done in previous courses, f of b minus f of a over b minus a. It has the exact same structure. We've just put x here instead of b. If you recall, this expression was the average rate of change in f over the interval ab. So slope of the secant, difference quotient, and average rate of change in the function over an interval are all the same concept. So and that's actually, I think, what I've said here. So slope of the secant could be expressed in either one of these forms. Top one we usually refer as the difference quotient, and then the bottom one you could refer to as the average rate of change over the interval ax. Okay, so let's try this with a couple examples. So we want to do simplify the difference quotient for this function. So first thing we need is f of x plus h. So plugging x plus h into that function gives us 3 times x plus h squared minus x plus h. And again, notice this minus sign, when I'm plugging the x plus h in, that negative has to apply to the whole expression. If you're struggling with where I got that from, remember, think of these as input boxes. And I'm putting x plus h into the boxes. Okay, so now we can FOIL this. So 3 times x squared plus 2xh plus h squared. Then distribute minus x minus h. Distribute the 3. Alright, we have that. And we don't have any like terms here that can be combined, so that's as good as that gets. So we're going to now do f of x plus h minus f of x. So we're going to take all of that, and subtract the function. This is again another situation where you got to use parentheses here. This is the first part, and then we're subtracting the function, meaning this entire thing. This is f of x, 3x squared minus x. Has to be put in parentheses, right? We're subtracting all of f of x. Right? This whole thing represents f of x plus h minus all of f of x. Almost all the mistakes are made right here, not remembering to put parentheses around that second one. Okay, so now we do have simplifying that can be done. At this stage, you're typically going to get a good amount of cancellation. So you'll notice if you distribute this negative through, this is going to cancel with this term. And then you have minus a negative x, which makes this a plus x, which will cancel this term. So the only thing that is left are these three terms here. So we get 6xh plus 3h squared minus h. Now, for this type of problem, when you have a polynomial, one way to know if you've done it correctly is when you get to this stage, everything should have an h on it. If you have any terms left over that don't have an h, you've made a mistake somewhere. Okay, so now we can write the difference quotient. So we've got f of x plus h minus f of x all over h. So we're taking that expression, that's the numerator, and dividing it all by h. And as we've said, they all have h on them, which means you could factor out an h. Be careful when you factor this h out, there's still a 1 there. And then these two h's cancel. So you end up with 6x plus 3h minus 1. And that is our simplified difference quotient. Alright, let's try the alternate form of it. So for this one, it's much easier to just get this written out. You can go straight to it. So f of x is just, here, let me write this first. So f of x minus f of a all over x minus a. Okay, so we know this is x cubed minus a cubed over x minus a. So that's it. It's plugged in. But we need to simplify it. So here you have several options. If you remember the formula for the difference of cubes, so I'm actually going to write that up here. Actually, I think we started. So back when we did this in Algebra 2 or college algebra, we had x cubed minus y cubed. We know that it factors as x minus y. It starts off the same, meaning the same sign here, but no powers. And then for the quadratic part, you have x squared, and then it's always the opposite sign of this, plus, and then it's these two multiplied together, xy, and then plus the last one squared. So if you have that memorized, you could go straight to that. So in this, if we apply it here, we have x minus a times x squared plus ax plus a squared all over x minus a. So then you can see these two things cancel, leaving us just with x squared plus ax plus a squared. Now there's a good chance that maybe you forgot this factorization, so you don't give up. We have another option. We actually have two other options. We can use long division, or we could even use synthetic division. Let's do long division though. So we have x minus a out there, and then we're going to put the this guy in, so we have x cubed, and then remember it's best to put in placeholders for the other powers. So we have plus 0x squared plus 0x minus a cubed. So I've got the 0 places filled just to make it easier for things to line up. Okay, so as we go through this, we say, what do we have to multiply x by to turn it into x cubed? Well, x squared. So then you distribute this to both of these, so it'll be x cubed and then minus ax squared. Subtract down, these cancel, but then you have 0 minus a negative ax squared, which makes it ax squared, and then the rest of it drops down. Okay, and then we just go again. What do we have to multiply this by to get that? Well, that would be a plus ax. Distribute it, so we have ax squared minus a squared x. Right, this times this would be a squared x. And then that's all those. Subtract down, these cancel, but you end up with a positive a squared x minus a cubed. Okay, and then the last one, what do we have to multiply that by to get this? Well, just an a squared. And when we distribute it here, we get a squared x minus a cubed. And when you subtract on this one, it all cancels, you just get 0. Remember, that is your remainder. This is your quotient then, and that's what we're getting here. When you take this and divide it into this, you just get the quotient. So much more work, much easier to have this memorized, but both methods work. So in the end, though, that was our final answer for that. Okay, last thing we're going to look at is symmetry. So we have three types of symmetry that we might see. We could see a graph could be symmetric with respect to the y-axis. What that means is if you fold the graph over the y-axis, it would fall on itself. Algebraic way of testing that is whenever you have a point xy on the graph, then the point negative x, positive y would also be on the graph. That's what it means to be symmetric about the y-axis there. All right, then symmetry about the x-axis. So similar idea, if you fold it over the x-axis, it falls on itself, or whenever the point xy is on the graph, the point x negative y is also on the graph. Now we don't see this as much because we're typically dealing with functions of x. Later on in the year we will start dealing with graphs like this, but at the beginning this is not going to be as common. So this never can happen if it's a function where it's a function of x, y is a function of x. So we're going to see this much more often than this. And then the final type of symmetry is symmetry about the origin. So this is rotational symmetry. If you rotated this 180 degrees, the graph would fall right on top of itself. Right, this point would rotate right down to that point. So the algebraic way of saying that is whenever xy is on the graph, negative x, negative y is also on the graph. Now, like I said, these are the two most common symmetries that we see, and we have another way of characterizing them, which is the concept of an even function and an odd function. So an even function is always symmetric about the y-axis, but another way to state that is f of negative x equals f of x always. Now this comes directly from the definition that we said before, because we said for it to be symmetric about the y-axis, whenever y is on the graph, then that implies that negative x, y is also on the graph. When this point's on the graph, then so is this. Now that means these two y values have to be the same, but the y values are f of x's. So this is saying that this point here, f of negative x, which is what this y value is, has to be the same as this y value over here. They have to be equal to each other. So that's why even functions are symmetric about the y-axis. Okay, so we see an example of that over here. This function, whenever you plug a negative into this, let's actually just do it. F of negative x, if we plug it into that function, would be negative x to the fourth minus 2 times negative x squared minus 20. Right, if I simplify this, the fourth power is going to wipe this negative out on that term, so that's just x to the fourth. Then the even power here is going to wipe out that negative, so it's minus 2x squared minus 20. And this is the exact same thing as the original function. It's still f of x. F of negative x equals f of x, which means it is an even function, which means it is going to be symmetric about the y-axis. Okay, I guess we just did that one, so I don't need to write that again. Right, if you didn't get that copied down, this is the argument for that. So this is the way I would want it written. You could then put your conclusion, therefore f is even. All right, let's try another one. So g of negative x. So now what a lot of people get in the habit of is they think, oh, if I see an even power, it's an even function. This one has an odd power, so it must be an odd function. Well, it's not quite that simple. There is a problem with this one. We will see it is not actually odd. But we're going to start the same way no matter what, g of negative x. So this is negative x cubed in parentheses minus 3 times negative x plus 1. Now we have a negative raised to an odd power, which means this negative is going to survive. And if you're not clear on that, then just write it all the way out. These first two, if I leave that first one out in front, these two are just going to give you x squared, and then you get negative x cubed when you finish it. So the negative comes out of the parentheses. Here, the two negatives cancel, so you get plus 3x plus 1. So then you come back and you compare that to the original. Does it equal the original function? You can see it doesn't. It does not equal g of x. So what this proves is that it's not even. If these were equal, then it would be even. So therefore G is not even. But we still haven't addressed odd. So the definition of odd was we would have to have G of negative x being equal to negative G of x. I'm going to put a question mark because we have not established that. But we would need to test this. So we already know G of negative x is sitting here. We need to find this. So let's do that over here. Negative G of x. Well, that means applying a negative to the whole thing. So we can distribute the negative through negative x cubed plus 3x minus 1. So now we compare this one to this one. Are these two the same? Almost. They start off the same, but then this part here does not match this part here. Those are different. So this is not equal to G of negative x. Right? We don't want this to equal the original. We wanted this to equal this in order for it to be odd, but they're not the same. So therefore, G is not odd. It's neither. It's neither even nor odd. So it does not have any. It doesn't have the symmetries that we were talking about. We need to be careful though, because this function does still have symmetry. I don't want to get too confusing here, but it's cubic, so it has a point of inflection somewhere. We could locate it, but let's just do this. So it is not going to be symmetric about the origin, but it is symmetric about its point of inflection, meaning that if you rotated it about its point of inflection 180 degrees, it would fall on top of itself. But we're not going to be concerned with that. So right now we're just concerned with symmetry about the origin and symmetry about the y-axis. Those are the only two that a function can have. All right, I believe there's one more. Okay, yes. All right, so the process again, same as all of them. Start with h of negative x. So this is 1 over negative x cubed minus negative x. If we simplify this, it'd be 1 over, that negative's going to come out in front, and then that negative's going to cancel. Are these the same? They're not. Not equal to h of x. So therefore, h is not even. That also tells us, therefore, h is not symmetric about the y-axis. Right, if it's not even, it can't be symmetric about the y-axis. Okay, then let's check to see if it's odd. So to see if it's odd, we need to come back and look at negative h of x. That's just negative out in front of the whole function. But when you have this negative sign, you can either apply it to the top or you can apply it to the bottom. So to convince you of that, think of it this way. It's the negative is really like negative 1, which I could write as negative 1 over positive 1. But I could also write it as 1 over negative 1. I could put the negative in the top or the bottom. And then when you multiply across, I'm going to just distribute that negative through the bottom. So the top is still 1. It's negative x cubed plus x. And notice those are the same thing. This is equal to h of negative x. We have negative h of x equals h of negative x. And that means it is odd. So that implies h is odd. It's an odd function, which means therefore h is symmetric about the origin. Alright, I believe that is the last example, so hopefully this is helpful. If you do have any problems with the assignments, make sure you are sending me emails about those. Alright, we'll see you guys in the next one.